Hi, I'm Zor. Welcome to Unizor Education. I would like to talk about linear functions today. Seems to be like a relatively simple topic. However, there are many, nuances which you probably should know, and they're quite interesting actually, even from historical perspective. Well, what can be simpler than linear function? Something like this, right? Well, obviously. It is a simple function. However, I would like to point out certain peculiarities and properties of these functions, graphical representation, etc. So let me start from certain definitions. Well, there is a certain duality in the concept of what linear function actually is. There is an abstract, more, I would say, purely mathematical aspect of linearity. It means basically the following. We can consider function to be linear in this abstract sense. Let's say you have a function f of x. Now, let's assume x is just a number, let's say a real number. So the concept of linearity in its abstract sense says the following, that the function is supposed to be considered linear if the following is true. So, these are just numbers. So u and v are numbers where the function is defined. Now, if you will multiply u by some factor and v by some factor and combine them together in this expression, then the function, if it behaves this way, then it can be called a linear function. Now, an example obviously is something like this. Well, indeed, if you will combine 2 of au plus bv, obviously it's equal to 2au plus 2bv, which is equal to a2u plus b2v, right? So this becomes f of u, and this becomes f of v. So this property of linearity, abstract linearity, is preserved in this particular function. Now, how about a different function which we also used to call linear, at least in high school? Something like this. Is this function linear in this abstract sense? Well, let's just calculate. 2 times au plus bv plus 1, right? Now, that's on the left. On the right, you have 2 times the function of u, which is the function of u is 2x plus 1 plus b, sorry, it's not x, it's u, plus b to v plus 1. Now, are these two equal to each other? Well, let's consider this is, let's open the parentheses, bv plus 1. Here, if we will open the parentheses, it will be 2au plus a plus 2bv plus b. Obviously, it's not exactly the same as this one. So, this function, in this abstract sense, is not linear. However, what I would like to say right now is the following. Usually, this type of function is considered to be linear in high school and in some other places, and I will talk about why. The abstract linearity concept Well, you just probably should remember it if you want to, but usually we will not be talking about linearity in this more strict sense. We will be talking about linearity in this sense, which basically means that this is some kind of a polynomial, and the highest degree of the polynomial is 1. And then quadratic functions will be those polynomial functions where the highest degree of the argument will be 2. So, forget about abstract linearity equality, and let's concentrate on this step. So now I can define a linear function in this, I would say, more elementary, if you wish, sense. I don't know how else to qualify this particular thing is. But basically what I would like to say is that the function of type ax plus b, where a is not equal to 0, this is a mandatory requirement, a is not equal to 0, we will call linear function. Now, a little later I will talk about why a should not be equal to 0, but basically understand that the function is not really the same if a is equal to 0, which means it doesn't really depend on argument, it's constant b. So it's still a function from the strict definition of the function, but it's not interesting function to research or to analyze, and it doesn't have many properties with which this function, where a is not equal to 0, does actually have. And we will talk about these properties. Now, if b is equal to 0, by the way, let me just for 1 second return back to abstract linearity concept. If b is equal to 0, then function a is equal to ax is linear in this abstract sense. Well, indeed, if y is equal to ax, then a times au plus bv is equal to, let's open the parentheses, it will be aau plus abv, which is the same thing as aau plus bav. So these are exactly, if you remember, f of function f of u and f of v. So basically we can open these parentheses and put it outside of the function, and that actually means that the function y equals a times x is linear in this abstract definition. However, again, let's forget about abstract. I always promise to forget about this for a while and then I return to it, right? Alright, so anyway, this is the functions which we will be considering. A can be anything which is not equal to 0, b is anything. Now, anything means what? Well, it can mean integer, it can mean rational, it can mean irrational, or whatever. Now, traditionally, and that's exactly what we will be considering, I will consider a, x, and b to be real numbers. Real. Not integer, not rational, real. It can be complex, I mean, in theory there is nothing to prohibit us from this, but this is not what we will be dealing with. We will be dealing with real functions. So, real linear function, or just plain linear function, as I probably would, skip the word real, means that argument is any real number, and coefficients a and b are any real numbers except a is not equal to 0. That's so much about definition. Now, so domain of this particular function with any real a and b and a not equal to 0, obviously domain can be any real, all real numbers. Because all real numbers can be multiplied by some real number and added another real number, which means the function is defined on all real numbers. Now, that's the definition of the function. That's the domain where it is defined. How about the range? How about the codomain? Well, obviously, the codomain in general is also all real numbers, but are we reaching every real number using this function? Is for any real number, we can have an argument which would be converted into this real number by this function. Well, let's just think about this way. Let's take any real number r, and let's assume that x is equal to r minus b divided by a. By the way, this is one of the reasons why a should not be equal to 0, because otherwise I cannot really construct this. Now, let's take this particular x and substitute it into the function. So what do we see? Y is equal to a times this x, which is r minus b divided by a plus b. What is it equal to? Well, obviously a and a are reduced, so it will be r minus b plus b, which is b and b reduced, which is r. So if x is equal to this, where r is any number, any real number, and a and b are, they define our function, then the function will take the value r, which means we can reach, using this function, any real number. So if these are real numbers and these are real numbers, first of all, function can be defined for any one of those. That's obvious, right? What also I'm saying is that for any real number r, I can find the prototype. It's this one. So any real number can be reached, which means that the range of this function, all the values of this function, they cover entire space of real numbers. So the domain is entire space of real numbers, and the codomain is entire space of real numbers, and the range of the function is entire space of real numbers, which means every number can be reached using this function from some kind of a prototype. So that's important. Now let's talk about a little bit more interesting property of this, which is very much related. What we are saying right now is that if this and this are sets of all real numbers, then the function ax plus b, where a not equal to 0. Now this function is defined for every number here, and its values cover an entire space of real numbers. Question is it a one-to-one correspondence? Can we establish one-to-one correspondence between this set of real numbers and this same set of real numbers using this particular function? I mean, we know that from here you can get there, and from any there we can get some prototype argument here. But is it one-to-one correspondence? Well, since we can always define these, we can say that any number from here corresponds to some number here. All we have to do right now to establish one-to-one correspondence is to prove that this is impossible. We cannot take two different numbers from the real, from the set of real numbers, using this function, arrive to the same value. If I will prove that we cannot arrive to the same value, it means all of these guys are different. Whenever these are different, these are different. And since I already know that they cover an entire space, and for every one of them there is a prototype, that would prove that this is a one-to-one correspondence. So all I have to do is I have to prove that I cannot take two different real numbers, apply my linear function, and get the same value. Well, let's prove it. Let's assume there is a pair of real numbers, u and v, which, substituting them into this function, where a is not equal to 0, obviously, would result in the same number. So au plus b equals to av plus b. Is it possible if u and v are different? Well, let's just think about it. Now, these are equals, right? So from equal, if we subtract equal, we will get equal. Remember this, right? So let's subtract minus b from both sides. what I will have is AU is equal to AV. Now, if equal values divide by the same not equal to 0 value, we will get equal. So let's divide by A, and I will get U is equal to V. But I have assumed that these are different. Now I've got it equal. So it's a contradiction, which means we cannot get into the same value from two different arguments given. Which means we have established a one-to-one correspondence between sets of real numbers and itself, the same set of real numbers, using this function. For every real number argument, there is one and only one value. For every value, there is one and only one argument, which can be used as an argument to this function to get that value. This is a one-to-one correspondence. Okay, that's fine. Next. Have this plan on the left. What's left? One-to-one correspondence. Monotonic. All right. Another property of linear function is that it is monotonic. Monotonic. Well, I'm sure you understand what it means. Basically what it means, let me just repeat it. It's always increasing or always decreasing, basically. More precisely, first, case A greater than 0. Then, if U less than V, then AU plus V less than AV plus V. So, the value of the function would be greater if the value of argument is greater. Well, how can we prove it? Well, it's basically very easy. Let's think about it. If U is less than V, and then we multiply a smaller number by some positive number, then the result will be smaller, which means AU will be less than AV. Now, if you have two numbers, one is less than another, and we both are, to both we are adding the same number B, well, obviously the result would also be smaller. So, starting from the smaller argument than another, we multiply by a positive real number A. The result also would be smaller, and then we add some number. It doesn't really matter, by the way, positive or negative. If one number is smaller than another, we add the same value to both of them. The result will be also smaller than this one. Now, what does it mean? It means that if A is greater than 0, function is monotonically increasing its value. As the argument is increasing, the function is increasing. Argument is increasing, the function is increasing. Now, very, very similarly, let's consider A is less than 0. Well, from this, we multiply both sides of this inequality by a negative number, and that actually changes the sign of inequality. If you have a smaller number and a bigger number, but then you multiply it by, let's say, by -1, then this number becomes bigger and this number becomes smaller. They are positioned on the different sides of the axis, of the numeric axis. And then again you add the same number to both sides. So from this, next is AU is greater than AV, and then AU plus AU plus B would be greater than AV plus B. So what's important here is, if A is negative, then the inequality is flipped whenever we multiply it by the same number A. Now, in this case, function is also monotonic, but it's not monotonically increasing. In this case, it's monotonically decreasing, which means the greater argument corresponds to a smaller function. So arguments are increasing, the function is decreasing. Okay. Now, the only thing which I actually wanted to talk about is why we so adamantly insist on a is not equal to 0. And I gave you already a couple of examples of the properties which are important for linear function. For instance, that the linear function establishes one-to-one correspondence between the real number, set of real numbers and itself. Monotonic property, like when argument is increasing, the function is either increasing or decreasing. Now, there is one more, again, more abstract consideration. Mathematicians are introducing sometimes new concepts, new types of functions, etc. So one type of a function is polynomial. Polynomial function. It's the function which is expressed as a polynomial, right? As a polynomial. Y is equal to a0 x to the n degree, a1 x to the n minus 1, etc., plus a n minus 1 x to the first degree plus an. Now, a0, a1, etc., an are coefficients. This x is an argument. Now, what is this polynomial degree? Well, it's n, right, in this particular case. But to really be the polynomial function of the nth degree means that a0 should not be equal to 0, right? Because if it's equal to 0, then it would be probably n minus first degree, etc. So if we want to really qualify a polynomial function as the function of certain degree, then the maximum degree x is raised into should have a non-zero coefficient. Otherwise, we can't really say that this is nth degree polynomial function. Well, from this perspective, linear functions are polynomial functions of the first degree. So these coefficients are equal to 0, but this one should not be equal to 0. Now, what is the function if a is equal to 0? Well, it's just the constant. From this perspective, all these are zeros and only a nth actually is left, which is x to the 0th degree, if you wish, right? So whenever you have a function which is equal to constant always for any argument, we can actually talk about this function as a polynomial function of the 0th degree. Not the first, 0th degree. So that's another difference. So from the polynomial functions specification, our linear functions should not have the coefficient a equal to 0, because then it would be just a different type of polynomial function. But this is just yet another consideration. The consideration before, like for instance, that we have established this one-to-one correspondence, are probably more important. And then, obviously, whenever you're talking about certain like equations which we have solved this particular equation, we chose the number r as a result, a real number which we would like to get if we will have to find whatever the argument is. Now, I basically told you that x is supposed to be equal to r minus b divided by a, right? How did I get it? Well, I've solved this equation, obviously. So whenever we will be talking about equations, obviously, again, this coefficient should not be equal to 0. So there are all these considerations, and that's why let's just assume that whenever we're talking about linear functions, a is not equal to, in this expression for a linear function, a is not equal to 0. Well, that's it for today. This lecture is just some kind of an introduction to linear functions. I will be talking about graphs and some other properties, but that would be in the next lecture. Thank you. I'm Zor. Welcome to Unizor Education. I would like to continue today talking about linear functions, and especially about graphs of linear functions. So we are talking about graphical representation of a function. Well, let me start with something which everybody knows, that the graph of the linear function is a straight line. I'm sure every student of high school or whatever knows that this is what it is. Well, but let me ask you this question. Can you prove it? Can you prove that the graph of the linear function is a straight line? Well, that's not such a simple question, because we really have to think about how to do it. All right, here's what I suggest. This is the coordinate plane. This is x, this is y, and our function is ax plus b, where a not equal to 0. It has some graph. How straight is it? All right, here is how I suggest to approach this particular proof. And again, by the way, there might be many different proofs. I'm just suggesting one of those. We all know from geometry that the shortest distance between two points on a plane is along the straight line between them, right? So if you have 2 points, then the shortest distance is along the straight line. Well, by the way, this is something which I have covered in geometry part, and you definitely can recall or go into this part and check how it works. Okay, this is one property which I would like to use to prove that the graph of this particular function is a straight line. Now, graph of this function goes through certain points, right? Point x is an argument, which is here, and y, as a result of this application of this function, would be here. This is x, this is y. That's how we basically draw the graph. What I suggest is the following. Let's have 3 points on the graph. Let's call it u, v, these are arguments, and w. These are values. This is a u plus b, this is a v plus b, and this is a w plus b, right? I would like you to recall another property. Again, it's geometrical, basically. It's the Pythagorean theorem. If you have 2 different points, let me just put another drawing, x, y, 0. If you have 2 different points, one with coordinates a and b, another with coordinates c and d. So this is a, this is b, this is c, and this is d. What's the distance between these 2 points? Well, obviously you can draw the parallel line here and here. It would be the right triangle, and this is hypotenuse, and these are 2 catenae. So this catetus is c minus a, right? C minus a gives you the length of this catetus. And this catetus is g minus b. So using the Pythagorean theorem, the distance between these 2 points would be a square root of square of this catetus, which is c minus a square, plus square of this catetus, which is g minus b squared. So square of a hypotenuse is equal to a sum of squares of 2 catenae. That's why this is the formula for a distance between these 2 points with coordinates A, B, and C, D. So I will use this to calculate the distances. So basically that's enough of the preliminary information which I need to prove that this is a straight line. And here is how. I will calculate the distance, let's call this U, V, and W points. These are lower cases, and this is upper cases. Now, I will check the distance between U and W, and then I will compare it with sum of distances from U to V and from V to W. Now, I know that from U to W, the distance is the shortest distance. It goes along the straight line. Now, if I will be able to prove that sum of these 2 distances is exactly the same as the distance from U to V, it actually means that V cannot lie outside of the straight line, because as we know, again, from geometry, it's the straight line which is the shortest distance. So if sum of these 2 distances is exactly the same as this, it's supposed to lie on the same line, on the same straight line. So that's why this is not the case. So all I have to do to prove that the graph is a straight line, I have to choose randomly, completely, 3 points. I call it U, V, and W at the argument. Draw or construct whatever 3 points on the graph, and check the distance between 2 extreme points and sum of 2 distances between the left extreme to the middle and from middle to the right extreme. Now, when I'm saying middle, it doesn't mean it's really in the middle. It's somewhere in between, basically, right? So 3 completely, no restrictions. Let's just assume that U is less than V and V is less than W for simplicity. And then, after I choose these 3 numbers, I substitute these 3 numbers to linear functions expression to get these 3 values. Now I have coordinates of all these 3 points. Now, having coordinates, I can find the distance using this formula which I was just talking about. And then I compare the sum of these 2 distances with the sum of the distances between U and W. So all I have to do is to prove that the distance from U, let me use the uppercase, the distance from U to W is equal to the distance from U to V plus the distance from V to W. I use the distance between 2 points as an absolute value, and these are points actually on the plane. U, V, W, these are points. So that's what I have to prove using the formula for the distance. If I do that, it means V lies on this line between U and W. So if I have any 3 points and connect the 2 extreme points with a straight line, the any point in between should also lie on it, which means it's one and only one straight line. So how can I prove this? All right, this is sorry, this is just a technical issue nowadays, right? So let's calculate what's UW, distance from U to W. Coordinates of the U are lowercase u and AU plus B. Coordinates of the W is lowercase w, AW plus B. So the distance between them would be square root of square of the distance between W and this plus square root plus square of the distance between 2 values of the y. So it's AW plus B minus AU plus B squared. This is UW. Okay. Well, let's simplify this. Obviously, if you will open these parentheses, you will have AW plus B minus AU minus B. So B will be reduced. So you have A, you can bracket it out, factor it out with the W minus U, right? So that's exactly what I will do. So UW distance is equal to square root of W minus U plus square plus A W minus U square. So I put square here and square here. Right? Square of this entire expression is square of this times square of this. Now I can factor out W minus U square, which means what? Which means square root of W minus U square, and in the parentheses will be 1 plus A square. Now equal. Now I will use the W is greater than U, so I can just put it outside of the square root, and that's what I will get. That's it. That's all I need. So let's put it here. The distance from U to W is equal to W minus U square root of 1 plus A square. Okay. Now we will do very similar operation with this and check what happens. Now, if I know how to calculate the distance from U to W, and this is this formula, and it's important that W is greater than U, so this is positive, then very analogously, the distance from U to V would be equal to V minus U square root of 1 plus A square. Correct? I mean, there is no difference. I mean, I'll just use letter V instead of letter W. What's important is that the first letter is greater than this one, and V is greater than U, right? Now, similarly, for V and W, from V to W, I will also use the same thing. Instead of U, I will put V. So it's W minus V square root of 1 plus A square. Now, we basically see that this sum of these is equal to what? V minus U plus W minus V square root of 1 plus A square. Right? Minus V and V, and we have W minus U, which is exactly the same as this. So this is a very easy proof that the line which really represents the graph of the function, linear function A is equal to AX plus B, is a straight line. I think it's important to not only know that this is a straight line, but also being able to logically prove that this is a straight line. The only purpose of whatever we are doing here is to basically to stimulate you to think about certain things logically. Don't take it just on the face value. If somebody told you this is a straight line, prove it. It's very, very important. That's what lawyers do. They prove the points, right? That's what doctors do. They prove that their diagnosis actually is correct diagnosis based on whatever symptoms they observe with the patient, etc. So there are many examples. What's important is never take anything just as a belief, as a kind of statement without any kind of a baking. The proof is always very, very important. Okay, so we have proven that the line which represents the graph is a straight line. Now, what about the graphical meaning of coefficients A and B? that's actually very important as well, and let me go into this. But this is something which I'm sure you've heard about. Again, the question is why. So everybody knows that A is called a slope and B is called an intercept, right? Intercept. Why? Okay, why A is a slope? Let's take two different values of argument. X is equal to A and X is equal to B. Then y is equal to, let's call it P. It's equal A plus B. And another y, let's say it's Q, is equal to this is a capital B. B plus B. Now, so we have two values of argument and two values of function. So let's just do this. We don't really do this way. It's confusing. Let's do the following. Let's compare the increment of the function relative to the increment of the value. So let's just for simplicity assume that A is less than B, these 2 points. So increment of the function is the difference between P and Q, right? So, which is AB plus B minus AA plus B. That's an increment of the function. Now, if I will divide it to increment of the argument, which is B minus A, what happens? Well, obviously, if you will open these parentheses, it will be minus A lowercase a and minus B. B would be, this is plus B, this is minus B, so you can just get rid of it, and you will have AB minus AA, A outside of the parentheses, so it would be AA minus, AB. So it will be AB minus AA divided by B minus A. Now A, you can factor out, it will be B minus A divided by B minus A. And as a result, you can reduce this, you will have A. It's not right. Get another one. A. All right. So that's why the coefficient A is called a slope, because if you will compare it graphically, let's use the same graph. We don't need the third point. So if you will take two different points on a graph, this is A, this is B, this is P, and this is Q. P being AA plus B and Q being AB plus B. Now, what we see is the difference between P and Q is this. This is Q minus P. This is increment of the function. From this value, it grew up to this value. That's the increment of the function. Argument is grew by this. So this is B minus A. So if you divide this into this, you get basically a slope, right? That's why it's called a slope. The steepness of the graph obviously is in this particular coefficient. The greater the coefficient A is, let's say it's positive, and the greater it is, the function would be monotonically increasing, but the greater this ratio is, which is A, the steeper would be the graph, because the function would grow by a greater degree relative to the increment of the argument. Now, if A is negative, then the absolute value actually of the A decides the same thing, then the function would be decreasing, but the slope, the steepness of the decrease would be the greater if the absolute value of a being negative, the absolute value of a would be greater. Because again, for the same increment of the argument, the function would either grow if a is positive or decrease in value if a is negative by a greater ratio. So that's why a is called slope. Now, what is b? Well, substitute into this x equals to 0. Now, graphically, if x is equal to 0, it's this distance. Which means that's where the graph intersects the y-axis. And that's why the b is called y-intercept. So this is the value of b. For a positive b, the graph intersects the y-axis above the x-axis. For a negative b, obviously the graph would intercept the y-axis below the x-axis. But in any case, the value of b is actually this particular value, positive or negative. That's why b is called intercept. So y equals ax plus b. A is a slope and b is called a y-intercept. That's it for today. That's all about graphs for linear functions, which I wanted to talk about. There will be some other properties of the linear functions, but that would be the other lecture. Thank you. Hi, I'm Zor. Welcome to Unizor Education. Continuing our linear function theme, we have discussed the major principles, definition, domain, etc. We have discussed the graphs, and there is one very important property of linear function which I would like to talk right now. This is proportionality. Now, what actually I mean in this particular case? Proportionality is a concept very much embedded in the linear function in a way that as you are proportionally increasing arguments, the function also proportionally increasing its values. Let me be a little bit more precise. And I think graph actually might help in this particular case. So if you have a straight line which represents the graph, and I will take 3 points, A, B, and C, with values P, Q, and R, and the function is ax plus b, where a is not equal to 0. Now, what I mean is that these are increments of argument. These are increments of the functions, the function value. So my point is that the ratio of increment is exactly the same, arguments or the value of the function. What I would like actually to prove more precisely, that the relative increment of the value of the function in 2 different points. So this relative to this should actually be the same as relative increment of the argument. From the geometrical standpoint, it basically means that these 2 triangles are similar. Since they are similar, then this catetus relates to this as this to this. So the similarity from the geometrical standpoint means this, algebraically. And obviously it's all related to the fact that this is a straight line. Were it not a straight line, obviously nothing like that would hold in general. So for any linear function, this is actually true. Now, how can I prove it? Quite frankly, it's very easy. Let's just think about what are P, Q, and R relative in this term, considering A, B, and C are arguments, and we will very easily come with this particular equality. Okay, R minus Q is A, C plus B minus A, B plus B. Divided by Q minus P. Q is the value at point B, which is A, B plus B minus P is value at A. Equals. What does it equal to? Well, obviously, if I will open these parentheses, now B would be here with a plus, here would be with a minus, and I will have AC minus AB, or AC minus B. Now, in the denominator, I will have a similar picture. It would be minus AA minus B, so B will be reduced, so it will be AB minus AA, so it's AB minus A. Since A is not equal to 0, I can reduce by A, and it's C minus B divided by B minus A. So this is an algebraic expression of similarity of these triangles from the geometrical standpoint. In any case, it signifies the proportionality of the increments of the function to the increments of the argument. That's very important. And obviously this proportionality depends obviously on this factor A and the fact that the whole thing is linear. That's why we can reduce all these formulas and prove this proportionality. Now, this is kind of an obvious property of linear function, but why did I ever talk about this trivial stuff? Well, there is a very important reason for this, and very practical one. This is a characteristic property of the linear dependency between argument and the function. So, if I have certain statistical results of some experiment, where on the input to some system I give one particular parameter and derive with the value of another parameter on the output of this system, then I'm changing my input parameter, my output parameter is also changing. I can check if dependency between input parameter and output parameter is linear or is not linear based on whether this particular property is observed or not observed. And I would like actually to go to a specific example, physical example if you wish, doesn't really matter which one, in this case it's physical, which would illustrate how people in science or wherever else can actually make a judgment about dependency between certain parameters, whether it's linear or not linear. All right, here is exactly what I mean. Now, let's assume you have some kind of a rigid reservoir filled with air. Now, here you have some kind of source of heat. These are supposed to represent the flames. All right? So let's consider this is some kind of a pressure cooker, and this is your source of heat. Whatever, it doesn't really matter. So what's important is it's rigid, which means it's really it really has certain shape which does not change. Now, and it's completely airtight. Now, as you increase the temperature, from the physical standpoint, you understand that the pressure inside would grow. Why? Because the molecules are moving much faster, and that's what actually means that the pressure is growing. So, people were definitely interested in how dependent the temperature of this particular container related to the pressure. So let's consider somewhere you have an instrument which measures the pressure. Here you have a thermometer which measures the temperature. And here are the results. So you have a temperature and you have a pressure. Okay, in my case, I check the pressure for these four temperatures. And the pressure in some units is 200, 300, 400, and 500. So let's just completely disregard what kind of units of measurements, whether it's Celsius or Fahrenheit or Kelvin, doesn't really matter. We're dealing with plain numbers. In some unit of measurements, these are temperature and these are pressure. Now, my question is pressure linearly dependent on the temperature? Well, let's remember that we have that property of proportionality between, if it's linear dependency, then it should be proportionality between the pressure and the temperature. So let's just check this proportionality. Now, the change between 50 and 60 is 10 units, and change between 200 and 300 is 100 units. So, the ratio is 10. Now, this change between 60 and 70 is also 10 units. Between 300 and 400 is also 100. So again, ratio between the increment of the function relative to the increment of the argument is also 100. And then the third ratio from 70 to 80 is also 10. From 400 to 500 again 100. So you have 10 again. So it looks like there is a proportionality between change of the argument and change of the function. So there is a strong indication, at least based on these four measurements, that the dependency is linear. Now, dependency is linear, and this ratio actually is the slope. So if I'm looking for for y is equal to a times x plus b, a is 10. That's the slope, because change of the argument results in a change of the function 10 times. So the only thing which I don't have is b, right? How can we establish it? Well, very simply. Let's just substitute x and y, let's say 50 and 200. So I will have y, well, which is 200. 200 is equal to a, which is 10, times 50 plus b. So this is 500, so b is equal to minus 300. Now, what if I will substitute these two, or these two? Well, obviously I must receive exactly the same result, otherwise I did something wrong. But let's just check. For instance, I put 60 and 300. So 300 is equal to 10 times 60 plus b. Now, what is b in this case? This is 600, this is 300, so it's minus 300. The same 300 as here. Well, 70 would be, what, 400 is equal to 10 times 70 plus b. 700 minus 400, again minus 300, and same thing over there. So obviously everything is held. So my equation is minus 300. So my equation is y is equal to 10x minus 300. That's the result of my analysis based on all information which I have, and I have only 4 measurements. I can actually derive the equation which connects these in this way. But the first and most important was I checked the proportionality to make a decision whether there is a linear dependency or there is none. So now, let me make another example, and then we will decide whether there is a proportionality there or not. Okay, here's an example. Let's assume I have the same table where I measure my pressure at this temperature. But instead of a rigid container, as I used before, I will use a balloon. Now, balloon is expanding as the pressure is rising, which means pressure will rise a little bit less than in case of a rigid balloon, rigid container. So as the temperature rises, the rigid container is preserving the volume, and the molecules are moving faster, and that's increasing the value. The rubber balloon is expanding, so the molecules have more room to grow, so the volume also is changing. And obviously the pressure depends on the volume as well. As the volume grows, pressure usually is going down, right? So increase in the pressure should be not exactly the same as in case of a rigid container. Now, I suggested to use the following measurements: 150, 200, 260, and 330. So, as I promised, the pressure grows not as much as in the rigid container case. Now, let's check exactly the same thing. Do we have a proportionality or not? Now, 60 minus 50 is 10. That's the change of the argument. Now, the change of this is 50, from 150 to 200. So the ratio is 5. Next, from 60 to 70 I also have temperature raising by 10. But here I have by 60. So my ratio is 6, 60 to 10. Next, from 70 to 80 again, my temperature is changing by 10. My pressure is increasing by 70, from 260 to 330. So ratio of the change of the function to the change of the argument is 7. So as you see, here we have different ratio. Now, that alone, I mean, considering the numbers are pretty different, it's not like 5.001 and 5.002, they are very, very close and can be explained as some kind of errors. But this is not an error. These are really dramatically different numbers, which proves that in this particular case, there is no linear dependency between rising the temperature and rising the pressure. And the reason for this is physical, obviously, because the balloon is expanding, so volume is changing, and volume is just yet another very important factor in changing the pressure. So, well, basically, that's it. That's all I wanted to talk today about. And what's important is to understand that the characteristic properties of the linear function can actually be used in practical life, and they are actually used to get to some kind of maybe physical or whatever the practical implementation is, dependency between arguments and the functions. By the way, in this particular case, what's important is there is a real physical law which is kind of in foundation of whatever I was just talking about. So if you have all three variables changing, the pressure, the temperature, and the volume, there is a law that this is constant. So if V is constant, then P is proportional to T. Because if P over T is a constant, then that's basically what it means. That the P is a linear function of T. But if V is involved as well, that actually changes this direct dependency, and it actually introduces this new factor, the volume from which pressure depends upon. But this is all physics, so it doesn't really matter. What's important is the characteristic properties of the linear function are very helpful to determine physical dependencies between certain things, between certain physical parameters. All right, so that's it for this particular lecture. Thank you very much. Next, probably I will talk about quadratic functions, I hope.